Good morning, this is Dr. Turner for Integrated Math 2. Today we are covering the last of Unit 9, which is problem solving with constraints. The fun thing about problem solving with constraints is that this is everyone's favorite type of math problem, which is word problems, unfortunately. So we're going to go ahead and get right into it. Now, the thing to note about doing these word problems, unfortunately, is that even if I were to do 100 million examples for you guys, there are always going to be other types of problems. So students typically in a non-AP or not advanced class get very used to saying, okay, this is my exact example and I'm going to copy this and do a problem that looks exactly like it. Unfortunately, with the word problems, that's not the case. So we'll just do kind of a few common ones that are going to come up on your assignment and that have been common to come up on like the standardized test or the CASP. Again, even in the assignment, I'm not going to do 50 different examples because you need to be able to apply what you know to the word problem. So this is going to be a little bit of a challenging section, and I apologize for that, but hopefully it won't be too bad, okay? So let's go ahead and get started here. One common example involving area and volume is to take, let's say, a piece of wood, and we're going to cut this wood. We want to make a box, okay? So we want the dimensions to, of course, be even as we're cutting out this box, and we're not going by my drawing, of course, here, but trying to cut the box into even pieces along the side. So imagine that each of these has the same width. So we're going to cut it this way. And then, of course, we're looking for a box, so we're going to need to cut it up and down as well. Again, pretending that each of those are the same dimension. Okay, then we're going to need to cut it going the other way, and we're trying to, use as much of this wood as possible so that we're not wasting anything. So we're going to cut it this way, and then those are going to be our dimensions. Now here, two of these pieces we're not going to be able to use, right? So these two pieces here, top and bottom, or the two on the bottom there, that we're not going to be able to use all the pieces because we only need 6 pieces to make the box. So we're using the length primarily in this cutout. For the 4 sides, it's going to be a longer box. And then the last 2 pieces down here at the bottom, those are going to be the sides of our box. So in a problem like this, you're going to be given dimensions for a piece of wood and then asked to calculate, basically what that is. So let's say for this box, let's say I have a width of, we'll call it, width, we'll call the width 24 centimeters, and for the length, we'll call this, call it 40 centimeters, okay? And so you want to be able to figure out the volume of a box that could be made using these dimensions. Now, again, not going by my diagram, but each of these, in theory, would have to be the same length because we're trying to create a rectangular prism. And so we're taking that 24 centimeters, we're cutting it evenly along 4 sides, which means each of these is going to be 6 centimeters in width. Okay. Now, to make the box fit, that would mean that over here, these little pieces that are going on the ends, these would also have to be 6 centimeters. So 6 centimeters here, 6 centimeters here. Okay. So the question is asking what's the volume that could be made from a box like this. So if we were to, and you don't have to draw this, but it might help to visualize it. If we were to take now these pieces, put them together to make our box, okay, then we're ending up with a box that looks something like this. And the dimensions of that box are going to be 6 centimeters by 6 centimeters by, here, this would be 34 centimeters. Where did the 34 come from? Well, the entire piece of wood was 40, and I had to cut off 6 to make the end pieces, so 40 minus 6 would give me 34 centimeters. Okay. Once you do that, you are looking for volume here. Volume of a rectangular prism is length times width times height. So either by hand or with a calculator, 34 times 6 times 6. That gives you 1,224. and we are talking about volume here. So remember, volume is always cubic units. So this is 1,224 cubic centimeters. So that is one example of problem solving with constraints, and you'll have a couple examples that look like that on your assignment. Let's say we go to another one. We have a candle that has a volume of, say, 24 cubic centimeters. And I'm going to give you dimensions where the height is twice the radius. And I want you to tell me the dimensions. Okay. So using this constraint, I want you to tell me what the height is. I want you to tell me what the radius is based on that constraint. That's the key idea. Problem solving with constraints. Okay. So looking here, volume formula, and you can draw a diagram if it helps, but the volume formula for a cylinder, which would be the case here for the candle, is pi times radius squared times height. Now, the constraint was that the height is twice the radius. I can plug in 24 for my volume, but just using that, I still have two variables. I can only solve if I have one variable. So using the fact that height is twice the radius, I can use that to substitute h for 2r. And by doing that now I have a formula that only has a single variable. So I can clean this up. I have a 24 pi, getting a little bit ahead of myself there. 24 pi, okay, 24 equal to 2 pi r squared times r is r cubed. And then I'm going to divide both sides by 2 pi. So r cubed is equal to 24 over 2 pi. And then I'm going to take the cube root of that value to approximate r. Now, most of the time, for my classes, I told you to leave it in terms of pi. Specifically with these examples, it's going to tell you to round to the nearest tenth. So again, with the calculator, let's do 24 divided by 2 times 24 divided by 24 divided by 2 and pi. Okay, and then I want that cube root. Okay, so depending on your calculator, you might need to switch it up a little bit here. That's fine. 24 divided by 2 times pi. Okay, and then I want the cube root of that answer. Which gives me approximately 1.563. You'll round to what it asks you to round to, in this case the tenths place, so this would be 1.6. And then the height here is twice the radius, so the height would be 3.2. As always with me, if it's a word problem, you're expected to write this out in a complete sentence. It doesn't need to be a long sentence, but a complete one, so you could just say in a short sentence, the radius of the candle is 1.6 centimeters, and the height of the candle is 3.2 centimeters. Right? It doesn't have to be a long, drawn-out sentence. Okay. Let's do one more example. Scrolling down here. Okay. So a lot of the questions are going to ask about maximizing or minimizing material. So for instance, there's a question here. A farmer wants to construct a pen using 100 feet of wooden fencing. What dimensions will produce the maximum area? So I have 100 centimeters of fencing, and I want to make a pen, and I want to maximize the area. So if I have 100 feet of fencing, this could be any number of dimensions. I could do 1 by 49, which around would give me a perimeter of 100. I could do 10 by 40, which would give me a perimeter of 100. I could do 20 by 30, which would give me a perimeter of 100. So there are a whole bunch of different ones that I can do for this. But in using problem optimization, and we'll talk about this more next year, but in problem optimization, the maximum is going to be in 2 dimensions, the one that is closest to being a square, and for 3 dimensionals, it's going to be the one that's closest to a cube. And you could do this by trial and error. If I find the area of each of these, this would be 49, I think we said feet, so 49 square feet. This would be 400 square feet. This would be 600 square feet. And the square is going to be the one that produces the optimal area, which is 625 square feet. So something to keep in mind. We will look at these a little more again next year. For now, you just want to be introduced to problem optimization. If you are still having trouble with it, that's okay. This is only one section, and then in Unit 10, we're going to be moving on towards something else. Okay, but that's it for today. If you guys have any questions, please reach out to me. Otherwise, have a good day, and I will talk to you soon. Bye.